Right, good evening, everyone. So I'm here to crush your cosmic dreams of life in the universe. No, I'm just trying to add some balance and some fairness and transparency to this discussion. I think many of us, of course, are optimistic and hopeful that there is life in the universe. But sometimes that optimism and bias, it is a form of bias, can lead us astray. And so that's what I want to talk about today, is just trying to keep our feet on the ground and give you an argument, or really break down some counter-arguments as to why it is that we could actually be the only ones in the galaxy, or maybe even beyond, maybe even in the universe. So we're going to start with some common arguments. I hear this all the time, and this is a great lead-off from the quiz, because we just had in that quiz, how many stars are there in the galaxy? And it was a gigantic number, 100 billion stars. So there's billions upon billions, as Carl Sagan famously said. And so when you think about that, you think, well, surely if there's billions upon billions of stars and planets in the galaxy, let alone the universe, then how can you possibly think that we are alone? One way to kind of visualize this mathematically would just a very, very simple version of the famous Drake equation. A simplified version of his equation would be to say the number of living worlds, NL, would be the number of stars, roughly, multiplied by the fraction of those stars that go on to have living things around them, FL. So this FL term is the thing that we don't know. We do know how many stars are in the galaxy. We can just go out with our telescopes and count them up. But how do we estimate FL? That's a really hard number from first principles to get. So we know this is 10 to the 11, and in order for there to be more than one, more than just us, then this would have to be 10 to the power of minus 11 for there to be more than just us. That's 1 in 100 billion probability. That would mean there'd be others out there. So that's kind of the argument people would often say. As I said, it's not just me. Listen to some other famous, much more famous scientists than myself tell you the same thing. I'm going to check the volume as we go here.
Do you think that there is life outside of Earth, intelligent life in the universe?
Absolutely, there is life elsewhere, and almost certainly intelligent life. It has to be. The odds are just overwhelming. There's 200 billion stars in this galaxy. Well, now it looks like every star has about 10 planets, so there's almost certainly intelligent life.
I assume it's the most frequently asked question, are we alone?
My best guess is that the universe is teeming with life.
There's surely other civilizations out there in the universe. There are 350 billion galaxies out there in the universe.
Okay, so you've seen the same argument, the same thing being said over and over again. And that's why probably my talk seems so out of place, because it's actually a much more provocative statement to go out and say, of course there's life in the universe. It sells better headlines. You're going to get invited to more TV shows probably if you say that. But I'm really trying to ruffle everyone's feathers a little bit and just push back on that. And Elon Musk famously jumped off on this a while ago. Of course, if Elon Musk says it, it must be true. So he said, in this tweet here, latest scientist predicts there's trillions of alien civilizations. And then this is really the key to this rebuttal. And Sean Carroll, a well-known physicist at Caltech, puts this very succinctly. That is not necessarily true. It really depends on what this FL number is. Why couldn't FL be 10 to the power of minus 100? Why couldn't it be 10 to the minus 50? Because if that was true, then it would just be us in the entire universe. And there's no reason why 10 to the power of minus 100 is any more or less likely than 10% or 1% or 0.1%. We have no idea what FL is. All bets are on the table. So it's just a very, very simple argument that you can deconstruct this numbers game. Yes, there's an astronomical number of stars, but there might be an astronomically small probability of life starting. That's, as far as we know, consistent with everything we know about the universe. So this is a difficult problem. Just to show you a kind of scale here, if FL was 1%, 10 to the minus 2, and we multiply it here by 10 to the 11, then there'd be a billion civilizations or a billion living worlds in the galaxy. But as I said, it could be 10 to the minus 11, in which case it's just us, or 10 to the minus 50, in which case the vast majority of galaxies are empty. there's no one in them, or you can keep going. This just goes all the way over. It doesn't really stop, right? You can just keep going. So this is kind of a problem. Until we have an idea of FL, you can't really claim this. So the second argument, someone would say, okay, fine, Kipping, I believe you. I can't use this argument, but you're saying that we're incredibly special. And astronomers kind of have a knee-jerk reaction to that. Because the sun is not special. There's plenty of stars like the sun. There's plenty of planets like the planets we have in our solar system. So why should we be special? And this is sometimes called the Copernican principle, after Nicholas Copernicus looked out and said, well, surely there's other stars out there, and they look fairly similar to our own. And so this seems to be the next good argument, also called the mediocrity principle. So Nicholas Copernicus shown here looking up, I'm sure this is not a photorealistic depiction, but kind of imagining him looking at the star and thinking about others out there. So let me just break down why this also doesn't work, okay? So let's imagine we do an experiment. We're all going to pick a ball out of a special urn that I have down here, okay? And anyone who picks a ball and doesn't pick a green ball, I'm going to kill. I'm going to shoot dead with, some, very perverse experiment we're doing here. We sometimes do this in the undergraduate classroom, but I've been told I can't keep doing it anymore. But we do this experiment, and then I'm going to collect all the people, all the survivors together. And of course, all the survivors must have picked a green ball because we got rid of everyone else who didn't. And now, for all of those survivors, you don't know anything except that you survived. That's all you know. You don't know about how many survivors there are. You just know that you picked a green ball. And I'm going to now ask you, how many green balls are in this urn that I've got down here? Given that you know the following. You know that you picked a green ball. And you also know that had you not picked a green ball, you wouldn't be here to talk about it. You wouldn't be able to even have this conversation, even have these thoughts. And I don't care how good you are at statistics, you're not going to be able to work that out. There's not enough information to work that out. It's an impossible problem. And it's really the same thing for the galaxy. There's all these worlds out there in the galaxy, and we happen to pick a living world to be on. But we also know, had we not picked a living world to be on, we wouldn't be here to talk about it. So it's the same problem. You cannot estimate how many living worlds there are based on your own existence. You're only here because you're here, right? That's kind of the problem. So we call this survivorship bias. It's a form of selection bias. Astronomers worry about selection bias all the time. If you look up at the sky, most of the stars that you can see in the night sky are not actually stars very similar to the sun. They're stars more like giant stars. It's not because giant stars are extremely common, it's just because they shine much brighter. It's a very strong selection bias we have, known as Malmquist bias in astronomy. The most common type of star in the universe is a red dwarf star. You can't see any red dwarf stars in the sky because they're too dim. But they are the most common type of star in the universe. That's another selection bias. And so here we have a very strong one. We're only here because we're here. So this isn't going to work. And I would just tell you that the Copernican principle fundamentally doesn't work whenever it concerns statements upon which your existence depends upon. It doesn't work in those cases. It's fine to apply it to things like Neptune. We have a Neptune. It's probably reasonable other solar systems have Neptunes. We'd probably be here whether or not we had a Neptune. But when you're talking about things that we depend upon for existence, then you can't use it. So I've demolished that one, and then the next one that sometimes gets twisted here is the emotional appeal. This is the one that kind of irks me the most. So, you might have someone like Professor Loeb here who would say something like this, it's extremely arrogant for us to claim that there's no other life in the universe, or extremely arrogant to assume that we're special. With the height of whatever, we must be humble and assume that we're not special. These kinds of statements, and these kind of statements bother me because they are making emotional appeals. They're basically saying, if you disagree with me, you must be very arrogant. And so that's already kind of setting it, that's not a logical scientific argument. That's an argument, that's an ad hominem attack, essentially, to the person who disagrees with you, preemptively. So it's going to be very hard to disagree with Professor Loeb if he stands at you and says, you're extremely arrogant if you disagree with me. And you're like, oh, I feel like I have to agree with him because I want to be considered arrogant. So this is not a good scientific argument in my book to start using emotions and characterization of the other party who disagrees with you. Now, I just say, when you look at this speciality thing, I tend to think of it more like snowflakes. Every single snowflake is different from every other. There's never been two snowflakes ever the same, and that's simply because the number of ways of arranging ice crystals is an astronomically huge number. So no matter, even if we live for another 5 billion years and it keeps snowing, we will never have two ice crystals, two snow crystals the same. And I would say the same thing is probably going to be arguably true or potentially true for chemistry. Chemistry is extremely rich, has a very diverse ways of creating things. It's quite possible that this speciality that we impose about ourselves is merely one part of a spectrum of all the different ways that chemistry happens across the universe. And any arrogance is the arrogance that we're assuming this type of chemistry is special. We're just a flavor. It's not the only speciality we impose upon it is our own ego, that this must be something different from all the other types of chemistry. So you can kind of push back about this arrogant statement and flip it over. So the next argument we might have at this point is you start to get desperate. We have 4 altogether. This is my third argument you sometimes hear. So, okay, fine, I believe you about these previous 2, but here's something you can't escape from. Life started quickly on the Earth. The Earth is 4.5 billion years old, but as far as we can tell, life got started very quickly. And when you look at that naively on its own, it does indeed seem quite compelling as evidence that life must get going all over the place. Here's the timeline very roughly of our home planet, the Earth. So let's say time equals 0 is when the oceans formed. That was about 4.5 billion years ago, or 4.4 billion years ago to be precise. About just less than 1 billion years after that, if I put on my marker here, we have the first microfossils that have been discovered. So we know that life was definitely on Earth by this point. It was presumably present before this, right? Because if life is sophisticated enough that it can leave microfossils behind, then there must have been some precursor to that didn't do this. So life probably got started somewhere in here. We don't know exactly where. Then we go all the way out to today, 4.4 billion years, and of course we have intelligence, however you want to define intelligence, things that can do statistics, in this case astronomy, think about the universe. We have creatures like ourselves are emerging at 4.4 billion years. You can actually push this around, say, 2 million years. Hominids have been around on the Earth for about 2 or 3 million years. If you push this 2 or 3 million years back, that's going back by 0.003 on this scale, right? We are very, very recent phenomena on this scale. Okay, and then I think what might surprise some of you is that the Earth will actually become uninhabitable to complex life fairly soon. Now, you may have heard that the sun will eventually evolve and engulf the Earth in like 5 billion years' time. You're like, well, 5 billion years, that's so far off, I don't need to worry about it, and that's true. But on a much sooner time scale, the sun's growing luminosity will push the Earth out of the habitable zone. It will no longer be possible for complex life. Probably some single-celled life will persist, but nothing like us, nothing that can think, that can wonder about the universe will be left after this point. So that's kind of interesting because we kind of emerged pretty late in the story. And if you open the book of Earth, the history of Earth, and you flip through it, you have life starting very, very quickly on the first chapter, and you have intelligent life emerging almost in the last chapter of that book. And that's kind of interesting in the timeline. So let's come back to this argument. People would look at this and say, well, this is the proof. Life started quickly. This seems like a good argument, therefore, that it should indeed be true that life starts common. Makes sense just on this scale. Here's the problem with this. So let's say life got started somewhere in this gap, and we know that it took this long to get to us, about 4 billion years, 4 billion years of evolution. That's going all the way from the very simple-celled organisms going to eukaryotes, combigenesis, all these developments that have happened in the evolutionary chain. 4 billion years to get to us. Multicellular organisms only happened 600, 700 million years ago. For the vast majority, it's just single-celled stuff out here, getting more and more sophisticated. Now, if this time if the time that it took on Earth, for the one example we know about, is typical. This is typically how long it takes a single cell to go all the way to something like us that can think about the universe, then the latest we could move this back to would be here, right? If life started here, there would still be time to get to something like us before the clock ends. Which means, given that we are here, given that we are thinking, living creatures, that in order for us to be living, thinking creatures, life has to start very quickly, because evolution is so slow. If it didn't start quickly, we wouldn't be here to talk about it. And maybe on most exoplanets, it does start much, much later than this. It's just that because it takes 4 billion years, they don't have enough time to get to us. We are the lucky ones where life just happened to get started quickly in that case. So if this is true, and we don't know that this is true, but if this is true, that this is the typical time that it takes evolution to get going, all the way to us, then the quick start to life is not actually interesting. If that's the minimum time it takes, how long it took on Earth, then life starting quickly is a requirement to our existence. It's a requirement. It is not an interesting fact to argue about that has anything to do with optimism for life in the universe. Kind of depressing. We can consider the opposite just very quickly. If, let's say, this was how fast it takes typically to go from single-cell things to intelligent things, which, you know, by the way, would be pretty surprising given Earth's history, because that didn't happen on Earth, then this is a completely different story. Now life could get going anywhere in this region and still have time to get to intelligence. So in this case, we would look at the early start to life and say, hey, that's actually interesting. That wasn't a necessary fact. It happened early. That's probably telling us that this is a quick process. Then it's reasonable to do something. But I think you'd be a hard sell to convince people that this was true. Because how come then on Earth it took 4 billion years for this to get going? Okay, so this is kind of the problem. So I would say in this case, the time needed was much less. Life starting quickly isn't a requirement. Then we could say something this is interesting. But as I said, this is kind of inconsistent with Earth's history. Now, as it happens, I actually did write a paper about this, correcting for all of these effects, going through all the statistics properly, dealing with all of these subtleties. And I'm just not going to go through all the work of it. I'm just going to give you the result. And the result is when you correct for all of this stuff and you really work it through, the probability that life starts quickly, it's a fast process, compared to being a slow process is 3 to 1, which is good news. So I'm not going to completely smash your dreams. There is a bit of good news here. As far as we can tell, the fact that life started early does slightly hint 3 to 1 odds, not 10 to 1, not 100 to 1, 3 to 1 odds. There is a hint that that is indeed useful information, and maybe indeed life does start quickly. Now the big caveat with what I did, and I can tell you this because I wrote the paper, is that all I could do is a thought experiment where we rerun time on Earth. Like you go back to the beginning of time and you let events play out again. Like the butterfly effect. You just slightly perturb things and see how things play out. That was kind of the thought experiment we did here. So it has to be pretty much exactly the Earth. On exact Earth-like planets, the same continents, the same amount of ocean, the same chemistry, the same, everything's the same. The same asteroids hit at the same moments. In that case, then I would say on those types of planets, life should indeed probably start quickly. But the big problem is we have no idea how common that is. And I can tell you this again as someone who works in exoplanets. We know of many Earth-sized planets. We are starting to find them. And we even are finding Earth-sized planets at the right distance from life, for life potentially. But you know, you've got things like this that happened in Earth's history. This is when the moon was formed. There was a planet about the same size as Mars that crashed into the Earth and led to the formation of our moon. And that seems to have been an important event in our history, let's say. And it's not clear how often that happens on other planets. Were we because apparently nowhere else in the solar system did it happen. We could certainly say that. Doesn't appear to be any of the moons like our own moon in the solar system that formed this way. So perhaps this is a really weird event. And many people think the moon forming event could be quite important to the story of why we're here in the first place. So those are all the arguments that we've covered so far. And the last one was the extremophiles. We also had this in the quiz, the tardigrade that can survive in space. And this might be your kind of clutching at straws a little bit argument here. You'd be saying, well, I'm optimistic because you don't even need an exact Earth. It could be a Venus, it could be a Mars, and you could still have life. Because I could take a tardigrade, I could put it on Mars, and it maybe might survive for 3 years or whatever. So maybe there's some optimism there. But I think we have to look at this. So let's do a vote. Which of these do you think is the correct, the most reasonable statement to judge from this? On the left, we have extremophiles can survive in extreme temperatures, pressures, acidity, salinity, etc., etc. Surely this proves that life can start anywhere. Whereas on the right, same thing, but we're saying surely this proves that life can thrive anywhere. So if you think the answer is A, raise your hand. If you think the answer is B, raise your hand. Yeah, so I would say B is the more reasonable deduction here. And really the problem is that a tardigrade and all the extremophiles are extremely sophisticated molecular machines. Very, very sophisticated things are going on inside their cells. This is a motor, a protein motor that's kind of dragging a cell behind it. I mean, this is all going on inside your cells and in even more sophisticated level inside extremophiles. Life did not start like this. When you have a pile of mud and water and a few bits of organic molecules hanging together, this was not the first thing that emerged by chance in that pool. This is the product of 4 billion years of evolution. Arguably, extremophiles are the most advanced life forms that we know about. So the fact that we have such extremely well-developed life forms now doesn't mean that they could possibly have been the first originators of what began on the Earth. Probably the very first things that got going were very fragile and could not survive much of a temperature range, a pressure range, an acidity range. Those are all mechanisms that life has developed over a very long period. So I don't think we can look at extremophiles and really say this proves, therefore, that life can start anywhere. Maybe it does, but I don't think extremophiles prove that. It doesn't disprove it, but it doesn't prove it. Okay, so we've kind of gone through all of these arguments, I've crushed all your dreams. And maybe the only thing you have left at this point is that I want to believe. And I totally get that. I want to believe that this is true. Let me hear what Carl Sagan said about this. Here's a good way of thinking about this. See if this plays.
Let's look a little more deeply into that. What is faith? It is belief in the absence of evidence. Now, I don't propose to tell anybody what to believe, but for me, believing when there's no compelling evidence is a mistake. The idea is to withhold belief until there is compelling evidence.
So he's saying that what is faith? Faith is belief in the absence of evidence. In the absence of evidence. I think that's a really good definition of faith. And I think in this case, we don't have any evidence for aliens, so any belief that you hold about alien life in the universe is a position of faith, vigorously. I would claim that's true. And it's okay to have a position of faith on that, but it is a position of faith. It's not a scientific belief that you can justify based on any evidence that we can point at. On the other hand, Sagan debating Sagan, Sagan also said that the absence of evidence is not evidence of absence. And that's also a very good point. The fact that we haven't received any radio signals, the fact that we don't see stars which have been transformed into engines in the sky, the fact that we don't apparently see galactic civilizations, none of that proves that there aren't out there. We can always think of ways that maybe they're just xenophobic, maybe they're shy, maybe we're all in a zoo. So it doesn't disprove it either, okay? However, I would say that everything we know about the galaxy so far is consistent with us being alone. That is consistent. Now, I would just say my real conclusion, the real point of this whole talk is to be agnostic on this, okay? You do not have, if someone asks you, do you believe there is life in the universe? You don't have to say yes or no. You can say, I don't know. And those three scientists at the beginning should have said that, in my opinion. If we don't have data to support a position, we shouldn't be saying, well, the answer is this. Because as a scientist or as a person or a scholar, we are expected to justify our answers based on evidence. That's kind of the whole point of science. It's evidence-based reasoning. There's no evidence in this case. And I would also claim that holding a position is dangerous. It's dangerous because it can lead to expectancy bias. So this is a well-known effect since the 1950s in psychological experiments. If a psychologist who's doing the experiment thinks they know what the answer is before they do it, they subtly influence their subjects, and actually you end up getting a repeat cycle around it. It's called verification bias as well. The most famous example of this I can think of is Percival Lowell, a very famous astronomer. And he wrote this in his book. He wrote that Mars is inhabited by beings of some sort or another we may consider as certain as is uncertain what these beings may be. I mean, this was over 100 years ago. He was convinced there was things living on Mars, absolutely convinced. And then what happened? He got to the telescope, he looked at Mars, and he started to draw these lines which he claimed must be canals. There must be a canal system on Mars. So for decades, people were convinced there was a canal system on Mars. It turned out Percival Lowell had one of the greatest eyesights of his generation, and he was actually seeing the blood vessels in the back of his eye. So that's how good his eyesight was. And he'd been told by optometrists that he had the best eyesight they'd ever seen. And so that was a reinforcement bias for him, that whatever he saw must be true, because my eyesight is so good. Of course, a few hundred years, 100 years later, we have this gorgeous image of Mars, and we know none of that was true. So having a position like that, believing something is true before you have data, can be very, very dangerous. So I would just say, to leave you, it's okay. It's okay to be agnostic, to withhold your belief about a scientific question until evidence comes either way. If you start sticking your foot in the mud and saying, I think this, it can be difficult to get your foot back out. Just wait for the evidence and we'll see. I'm hopeful there's life out there, but I want to see and collect the evidence to prove so. Thank you, everyone.